So here we will be doing some cache questions. So let's see. So this is one question, that is, find the number of sets and tag bits for a direct map cache with 1024 sets and a one word block size. The address size is 32 bits. So that means, if you see here, this direct mapped cache has 1024 sets. It's given 2 raised to 10. 1024 sets means 2 raised to 10 sets it has. That means how many bit would be there? I told you, in 2 raised to if you were having 8 sets, that means 2 raised to 3 sets are there. So the bits of set was 3. So similarly here, this was we did in the previous class, this theory part, okay? You have to understand that. So similarly, if you have 1024 sets, that means you have 2 raised to 10 sets. That means the number of set bits would be 10. And we know byte offset would be what? Byte offset would be 2 bits. We know that. So total bits are given to us is 32 bits. So from the 32 bits, if I subtract the set bits, that is 10, and my byte offset, that is 2, I will get 20 bits. And this 20 bits would be by what? My tag bits, right? Because we know tag, set plus offset bits would together give us total 32 bits. That is the address size, 32 bits. So if we got our tag and offset bits, tag we got as 10, offset we got as 2. So we can easily find set we got as 10 and offset we got as 2. So we can easily find our tag bits by subtracting it with 32. Understood? So the cache also uses a valid bit for each set to indicate whether the set hold a data or not. So there is a valid bit in set. That is, in each of the block, in each of the set, there would be one section which would denote the valid bit. Okay, that is V. If that V's value is 1, means this block holds a data. Yes. If this value is 0, means it is meaningless. That means the set holds no data. So if you look at this image here, this is something which you have to learn how to draw. This is a direct mapped cache with 8 set diagram. Okay. Now here, this is our cache, which has set 0, set 1, set 2, set 3, set 4, set 5, set 6 and set 7. Now how we are going to say is that each block has the data part, the tag part and the valid part. So this is something that you have to learn. That is, while you are going to represent the cache of 8-bit set, you will be dividing into 8 blocks first. Right? I will be dividing into 8 blocks. Then there would be one block, one part which denotes the valid bit, the other is for the tag and the other is for the data. This much we have understood. Now in the memory address, the tag, here there is tag, and then set will be matching to where set will be going through each of the set it will represent. Then offset bit, which is always 0 0. Okay. So here, if you see, you are going to see whether it is a hit or a miss. For that, we will take the tag part from the cache and the tag part from the memory and see whether they are equal, right? So, and also the valid bit, if there is data in that, their AND would decide whether we got a hit or whether we doesn't get a hit. And this part would represent just data. This is data bit, 32-bit data bit. Now tag would be what? If set is 3-bit and offset is 2-bit, the tag would be 27-bit. Okay, that is why tags part, that is 27-bit. So you have to understand here. We will take this cache 27-bit and my address 27-bit of the tag. We will see if they are equal and also the valid bit in our AND gate to decide if we get a hit or not. Okay, this is the logic. This is the logic. So you have to learn to draw this. That is the important part here. You have to learn to draw this. So if you see here, first there is our cache. This cache has a valid bit, tag bit, and the data part. The data part is the 32-bit data. Tag bit is only 27. That is what you have to understand, 27 bit, because in our memory address, if you consider, there is the tag bit which is 20 and set is 3 bit, right, and this is 002 bit. So 27 bit tag is there. Now this and this tag, we will see if they are equal, right? We will see they are equal, and also the valid bit also we will take and do the what? AND of that. We will do the AND of this operation to see if we get a hit or not. That is what we have drawn here. Fine. This you have to learn how to draw this diagram. So this is what here it is saying. The cache is constructed as an 8-entry SRAM. Each entry or set contains one line consisting of a 32-bit of data and 27 bits of tag and one valid bit. A cache is accessed using the 32-bit address. The two least significant bit is a byte offset, which is ignored for the word accessing, and the next 3 bit is set bit, which actually specifies the entry or set in the cache. A load instruction reads the specified entry from the cache and checks the tag and valid bit. So here, if the tag matches the most significant 27 bits of the requested address, if the tag of the cache matches the address's 27 bit, then the valid bit is 1. If all this condition is satisfied, that means it is cache hit. Means the tag in the most significant bit, that is 27 bits of the tag in our cache, and our address tag matches and the valid bit is 1, that means what? There is a hit. We got the data. Otherwise it is what? A cache miss. So you have to understand this logic. What is the logic? What happens? What should be the values to get a cache hit? So cache hit would be obtained so if we put the tag, if the tag matches the 27 bits of the tag, 27 bits of the cache and the 27 bits which is there in the our memory address, and also we have to make sure the valid bits value is 1. If in that cases, you will get the hit, cache hit. Otherwise it is what? Cache miss. Now let's solve an important question here. So similar questions can be asked, so you have to understand this is question which is there in the textbook. So first let's understand this question here. Loops are a common source of temporal and spatial locality. We know loops, we have learned it is temporal locality. Show the contents in spatial locality. Show the contents of cache after executing this code. Okay, so there is a code here where we have initialized the S0's value to be 5. To understand the code, you have to learn module 1. Okay, S1 is equal to given as 0. Now we have to see if S0 is equal to 0. If S0's value becomes 0, then we have to go to the done branch. Otherwise we have to take this instruction load, this instruction load, this memory access, this also is a memory access, and reduce the value to be S0 minus 1. Again do the operation loop. That means here 3 times the memory is accessed. 3 times memory access is there. And total how many times? This is a loop. So when the 5's value in S0, first we have initialized the 5's value to be S0, we have initialized first as 5. Now we will reduce each of them in each loop. So 5 times this loop would be there. So that means 5 times, and in each of the time load instruction means we will be accessing data from this address 4S1, 12S1, 8S1, right? So that means 3 times in each loop you are accessing the memory. So that means 5 times the loop is there, 5 times the loop is there, and in that 3 times you are accessing them from the memory. So 5 into 3, total memory access would be what? 15. 15 is a total memory access. Now, what would be the cache value in each of this? For that, you have to you have given that 0x4 is one address, 0x12 is another address, and 0x8. These are the addresses from which you are going to access for 12.8. Now, we have to find, this is direct mapped cache, right? It is given in the question, it is a direct mapped cache, right? So the question says that it's a direct mapped cache. So that means first we have to find the set of each of this address in our cache. So if I am drawing the cache, let's say this is my cache, some cache like this, let's say, and 0x4 means what? 0x4's binary form would be 0 0 0 0 1. Then rest for 32 bits is there, right? So thus you're going to put 0 0 because it is 0x4 means what? It would be 0x0 0 0 0 0 0 4. That is what it means, right? So each of the 4 bits you have to represent. You have to take only after this 2 bits represent what? Byte offset. The next 3 bits only would represent what? The set. So here 0x4 set would be what? 0 0 1. That means it belongs to set 1. 0 0 1 means what? Set 1. Okay. So you will be writing, this is my, let's say my set 0. So this would be set 1. In set 1, I will put what? 0x4. Fine. Now 0x12 means what? 0x12 first. Okay, now I'm not putting in my cache right now. That I will discuss it later. This part let me just clear. Fine. Okay. Now 0x12 set would be what? 12. How can you write it as? It's 0x12 we can't write. 0c would be in hexadecimal. 0c we will write in hexadecimal. So their value would be, C value would be what? 0 0 4 4 plus 8 1 1. Then rest would be 0. This is how you write it in what? In binary form of 0 as C. So that means this represent what? Byte offset. 110 would represent set. 110 is what? Set 3. So you have set 2 here and set 3 also you have. Okay, in set 3 0xc would be the. Now similarly if we do for 0s8, 0s8 would be what? 0s8 would be 0 0 8, right? 0 0, this is 0 1, right? So 0 1 0, then rest of the 0. This would be 0 as 8 we will represent in binary. So 0 1 0, 0 1 0 is what? 2, right? In our decimal. So in set 2 which would come? 0x8 would come. So that means I'm erasing all of this. I'm just writing only what we got as our final result. Here you have to understand, I found the 4's set as 1, 12's set as 3 and 8 set as 2. So if this is my cache, I have different blocks in my cache. Let us say this is set 0, this is set 1, this is set 2, this is set 3, set 4, set 5, set 6, let's say. So first what happened in set 1, first it will, this is our cache. So initially cache is like this, there is no values in cache, right? So first what happens, it will check whether in set 1 there is, set 1 is there any value of 0x4? No, set 1 is actually empty. So we got first cache miss. And we will put the value of 0x4 here in set 1. Okay. Now next we will access 12. So also that is in set 3. Set 3 is empty. So again we got 4, you got a miss. Again for 12 also you will get a miss. Initially at the first loop you get a miss at set. So in set 3 you have no value. So now you will add 0 as 12 here. Okay. Now next when I am accessing 8, it is in set 2. Set 2 is empty. There is no 8 in there. So that's why 8 is also miss. So now what I will put? 0x2 in the cache I will put. Now what happened? Now in the next loop, all of the value, that is 0x4, 0x2 and 12 is already there in our cache. So it is hit. it is hit. So the total misses would be what? 3 misses. The total memory access we have already discussed, it is 5. Right? Now if I am taking any loop already in set 1 and set 2, set 3, I have already placed the value, then we get cache hit. Understood? Only in the first iteration the cache was empty, so we add the values into it. So first 3 we will get what? Miss. Then later accessing and all, which is present, these data, later we are accessing the same thing itself. So this data is already present in our cache. That means cache hit would come. So here we have asked what is the miss rate. Miss rate would be what? The total number of misses is 3 divided by the total memory access is 15. 3 divided by 15 would give us what? Our miss rate. If you see here, first if you see total 15 iteration is there because 3 memory access load is there and total 5 iteration is there. So 5 into 3, 15 total memory access is there. The first time the loop execute, the cache is empty and the data, so first the cache is empty. So the data we have to fetch from our main memory 0x0, these locations, we have to get the memory and we have to put that value in our 1, 3, 2 sets respectively. This much we have understood. So in the first iteration 3 cache miss we have get. Now in the next 4 times the loop execute, we understood the data is now found in the cache because we have now put the values in the cache. So what would happen? Only 3 miss rate, 3 misses are there out of 12, 15 accessing. So that means 3 divided by 15, 20% into 100 if you do, 3 divided by 15 into 100 if you do, you get percentage. 20% is the cache miss rate. Okay, so this is the representation of that question. That is, here you have 0x4 in set 1, set 2 you have 8 and set 3 you have 12. Now tag bits are 0. Show the because if you see here it is just 0x4, then we said the rest of the bits here is 0, 0, 0. So the tag bits are all 0. That we have understood. And the valid bit is 1 for set 3, set 2, set 1. There is only data is there. Others valid bit is basically 0. This much we have understood. This is how we will represent that question. Now if you see this question, what is the miss rate in the following loop which is there? And the cache is initially empty is given. So here also it's an 8-word direct, that is 2 raised to 3 blocks are there. That is the thing. Now here what happened is that we are accessing the data in 2 locations. Again, the number of iterations would be 5, but the total accessing is 5 into 2. 2 load is only there, so you will be accessing only 10. Total memory access is 10 times. Now if you see 0x4's 3 bits we have to calculate. So 0x4 is like 0, 0, 1, then later all are 0, 0, 0, 0. So the 3 bit is 1, 0, 0. Now 0x24 if I am writing 0, 0, 1, 0, then 2 is 0, 1, right? 2 is 0, 1, 0, 0, 0, 0, like that. So first 2 bit are byte offset, 3 bit is 0, 0, 1. Both of them are going in set 1. 4 is going in set 1. This is also going in set 1. So that means what happened is that if both of them are going in set 1, in my first memory access I got 4 as miss. So what I will put in the, let's say this is my set 1, this is set 1. In set 1 I will put 0x4. Then 24 would come. It is again a miss. So what happened? I will remove this 0x4 and put 0x24. Okay, now in the next iteration I require 4 again, but here in the set 1 0x24, so I have to remove this, put 0x4. Now what happens? Next I need 24, so now again I have to remove 0x4 and I have to put 0x24, right? So that means in all iteration what we are getting is a miss. Here is conflict is happening, both of them are going in the same set, so we have to remove each one to put other, like that would happen. So that means the total miss rate is 100 because there is no hit. Every time we have to remove and put that, like that is happening here. So that is why here the miss rate is what? 100%. This is how the cache would actually work. I hope you have understood how the caches work. Now if you have any doubt till this much questions, please say it in the comment section. Thank you.